Okay, you guys, this is day one of 4.3. Okay, Riley? And we're gonna go a little bit off-road here. Hey guys, Matt, put that away, please. Can what? I don't think so. Okay. Okay, Alexi, where's your handouts? Yeah, you did. Girls, put your phones away. No, we're not doing that. We're doing Matt. You do. She just didn't hand them to you. Okay, you guys. You might have time to ask questions today, but it depends on you guys. Now, we're going to do the first derivative test today, which we did yesterday. So we're going to review that, review the maximum existence theorem. Then we're going to talk about concavity, which is not on any of the handouts. Then Monday, we'll come in and do the second derivative test. The way the homework is laid out is the first 10 problems are finding local maximums. The next 10 are finding where the function is concave up or concave down with inflection points. And that's where you stop on your homework, because that's all we're going to talk about today. So, what about the maximum existence theorem? You should be able to tell me, well, first off, what does it say? Well, okay, so this is a condition. We have to have what? A function that is what? Continuous. Okay, girls? And it must be on a closed interval. Wasn't talking to you. Okay, but what is the maximum existence theorem do for me? Now, there's 5 theorems. You got to know all 5. This is one of the most, they're all important. But if it's a theorem, it's important because there's only 5 of them. Okay, this guarantees, this is a guarantee, I like guarantees, that f of x has both a max and a minimum value. Yeah, I don't know what they call it, extreme value theorem. So you need to know what it does for you. Because then it promises that if I give you a function on a closed interval and the function is continuous, I can always find the absolute maximum and always find the absolute minimum. Okay? Right here. The maximum existence theorem guarantees this. Is that okay? Right, is that okay? Now, how am I going to use this? I'm going to look at conditions that must be met. We did that. Continuous closed interval. Where would I look? Where to look for maximum, minimum values? Where do we look for them? Okay, for the derivative, f prime of c does not exist. Okay, Alexi, what's another one? F prime of c is equal to what? Equals 0. Those are called critical points. Okay, James? Where there's 2 other places, endpoints. They are not called critical points. Okay? This is the extreme value thing. This is where you are going to look for max and mins. They will occur no other place except where the derivative is 0 or undefined, or at the endpoints. Critical points. Right? No, the critical points occurs with a function. Whatever function it is 0. So it could be the first derivative, could be the second derivative, could be the third derivative, could be the function. Those are called critical points, where the function is 0. Okay, so I locate these points, and then how do I know if I have a max or min? easy. Evaluate your function at the points. Whatever's biggest, that's the max. Whatever has the smallest value, that's the min. So you evaluate. That's why I like this then. Something that's not always easy, but f of x at the critical points and the endpoints. Okay, Alexi? We can find local max and mins. We did a little bit of it yesterday. We're going to formalize it today. And that's it. So when I get a continuous function on a closed interval, I like it because I know for a fact I'm going to have both a maximum and a minimum value. And I know where to look. And all you have to do is evaluate your function. Now, if you have not done the problems, that's going to be a problem for you because there's a lot of steps here. You have to identify if we meet the conditions, you have to find the places, and you have to evaluate. So if you can remember, you have to do 3 things. Maybe that'll help. Okay. What if we don't have a closed interval or we don't have a continuous function? That does not mean we don't have a maximum or minimum value. Sarah, put that away, please. Okay? I have to find another way. I can only find relative max and mins. Honestly, to find out if I have a global one, I have to have a closed interval or I have to know what the function looks like. I have to graph it. So the first derivative test, there it is all written out. We talked about it yesterday. And so let's actually look at this. So here's my first example. There's my function. At this c value, is that a maximum or minimum? It's a maximum. Now, using calculus, what's true about the first derivative here on the left side? It's positive, and then on the right side, it's negative. At the top, it turns out to be 0. If your first derivative is 0, you will always have a smooth function. That would be like driving your car and coming to a nice, complete stop before you shift it into a different gear, forward or reverse. It's always nice. So that's just a little hint. If they give you that, you know it's not going to have a sharp corner there. Now, by the way, if the first derivative, I should label that f prime. So what if the first derivative is positive, then what's true about my function? Just to review yesterday, because this is all there was. F of x is what? Increasing. That's it. If the first derivative is negative, then what's true about f of x? It decreases. So if you were absent yesterday, that's what you missed. Okay? Is there another situation here for a maximum? How about this one? Do I have a maximum at this c value? Yes, I still have a max. But that's okay, because what's true about the slope on the left side? It's positive. On the right side, it's negative, and I get a maximum because f prime went from positive to negative. The fact that the derivative is undefined here just gives me the shape of the function. Well, you got to be careful. You have to say it changes from positive to negative or negative to positive. That's correct. Positive to negative will be a max, and the minimum will be negative to positive. Did I say that right? And this is undefined. Okay, so let me graph minimums. So this is just a review from yesterday. Okay, there's a minimum, right? That's x equal to c. Minimum. What's true about the derivative? And I don't memorize this. I just draw the pictures. The derivative here is what? Okay, Declan, what's the derivative here? And this is f prime is what? F prime is negative. So it goes negative to positive. So that's what you say. F prime changes from negative to positive. I don't really care if the derivative was 0 or undefined. But when the derivative is 0 or undefined, I have a critical point. I have a point where I could consider to be a minimum. Key thing is the derivative is going to have to change sign. I have either one of them. Okay, there's your absolute value function. This is a minimum. What's true about the slope on the left side? It's negative and it's positive. So f prime goes from minus to positive. Nope. But this is f prime here is undefined. It's a place I'm going to look to see if I have a max or min. I know when I read the exam in the past, a lot of students will say if the first derivative or second derivative is undefined, then there's nothing there. That's not true. They always want the derivatives to be 0. No. You have to look at those undefined points. Think of your absolute value, folks. Okay. That's the first derivative test. That's it. That's all there is. Sign changes. Now we're going to go off-road because I don't, for some reason, have the information on us, but this isn't too bad to do. Okay. We're going to talk about the shape of the curve, concavity, and then we'll do a problem, and then I have a group activity for you. Concavity, that's the shape. This is said to be concave up. Why? Why is it hard? It's just up like a cup. Concave up like a cup. Is that okay? Tyler? Question? This is concave. Well, I was going to say like a frown. And then I even cheat here. Now, if you are concave, the function is concave up, you're up, you are happy. It's neither. That's why the yellow sheet. You can write on the white sheet, but the yellow sheet's just for you to write on. Now, if it's concave down like a frown, you are sad. You're unhappy, right? We're going to use a second derivative to do this. Let's look at the first derivative. There's two ways to do it. I prefer using the second derivative, but what's true about my first derivative is changing. It's negative, and it's negative, but now it's becoming closer to 0. What's happening? Now it's 1/2. Now it's 1. Now it's 2, but I'm giving you values. Cup. It looks like a cup. I don't care how you do it. My university students said they would concave up like a duck, like a duck's back. That's, they were kind of creative. Those were engineers. Not particularly. And yellow. There's a duck. There's the duck's tail. Okay. Math and art go together, actually. Okay, you guys, what's happening to, you guys, what's happening to f prime here? F prime is negative, it becomes 0, it becomes positive. Okay, Tyler, Jack? It's negative, it becomes 0, it becomes positive. F prime is doing what, Declan? You got the right idea. It's increasing. What about this one? It's decreasing. Now, I don't like that. By the way, it's perfectly fine. It's perfectly good to use on the exam. My problem with that is I get that confused with F increasing, decreasing. And if you don't read it carefully or write it carefully, you could get it wrong. If the first derivative is increasing, then the second derivative is positive. That's what I use. And that's okay because that's easy. Because if it's your concave up, you are feeling positive today. So F double prime is positive. If you're feeling down and you're wearing a frown, you're feeling negative. Usually it's negative. So F double prime is negative. That's the test I prefer. But you may use F prime increasing. I'm just saying we have 500,000 exams. It's easy for me to check this, and I have to think about this a little bit harder. But I usually write it down in my notes. So F double prime is negative. If you don't believe me that this is what happens when F prime decreases, make a table of values such that the slope is decreasing, and you'll take the slope again, and you'll see you get negative numbers. And maybe we can do it Monday if you want. Okay. Now, there's something else that happens when you are dealing with concavity. First off, what's the concavity for a straight line? No concavity. Oopsie. Okay, so now we were going to talk about when concavity changes. So if you had a graph that looked like this, it's concave down, then it becomes concave up. This point where it changes is called an inflection point. Have you heard that one? My guess is no, since I'm not hearing anything. You've never heard of an inflection point? No, not necessarily. I'm just asking. Okay, inflection point is a point on the graph. This is a definition where the function changes concavity. We'll get there. We'll look at those derivatives in a second. First, we have to understand what an inflection point is. It is a point on the graph. If the point's not on the graph, it's not an inflection point. If it's more than one point, it's not an inflection point. Okay, Lexi? This is not justification for an inflection point. More than that, what has to happen to the the second derivative? What's the second derivative here? We're concave down. So what's true about that? That's negative. What's true about here? You're concave up. F double prime is positive. How do you prove you have an inflection point, Noah? F double prime must change sign. Either goes plus to minus or minus to plus. Can't go to zero. It's got to go positive to negative, negative to positive. And when you are on the exam, and in my class too, when I give you quizzes or tests, I'm not going to let you say, hey, we have an inflection point because the function changed concavity. That's not good enough. You have to use the derivatives. Okay, they will not earn you a point. No point here. This is a definition of what an inflection point is. How do you know you have an inflection point? You have to look at the second derivative. Now, where might they occur? Yes. Definition. Sorry. Okay, so where do you think we might look for inflection points? Well, you're going to look for inflection points. You're not going to be given the graph. You're going to be given the derivative of the graph. We look for inflection points. If F double prime has to change sign, where would that happen? F double prime has to be what? 0 or undefined. Now, I've seen students on the exam say, well, the second derivative is undefined, therefore I can't have an inflection point. That's not true. That's not true at all. So be careful. If I give you an example of that, would be actually it would be y equals the cube root of x, because it looks like this, and then it looks like that. And at this particular point, at that particular instant, I have a vertical tangent at 0. So it's undefined. F double prime is undefined. Okay, these are called critical points. Critical points are where any function is 0. This is a function. These are critical points. They are simply candidates. No guarantee. So let's look at a couple functions. Some simple ones, and we'll do an example. So what if I have y equals 1 over x? Do you guys remember what that looks like? It's a hyperbola. Looks like this. Is there a change in concavity? This is concave down. It's curving down. This is curving up, even though you're going, the function's decreasing. That's okay. We're talking about the shape. And this is concave up. Are there any inflection points? No, because it would be at what value if it were there? At 0, but 0 is not on the graph. So you have to have a point on the graph. It has to be in the domain. It has to be a point on the graph. X equals 0 is not on the graph. I don't believe they're going to trick you with that, though. Probably. I have to sit and really think about that. But you can't, you have to, this would be your point. X equals 0 would be the candidate. However, X can't be equal to 0. It's not in the domain. Now, the derivative graphs do not need to be continuous. They could be discontinuous. Then the derivative wouldn't exist, would it? Okay, one more. Let's do this one. Y equals x to the fourth. Do you guys know what that looks like? That looks like a parabola. No, it looks like this. It's flatter. In fact, the higher your even exponents are, you get even more square. It's more and more square. Okay, what's true about that? Is that concave up or concave down? It's concave up. It's always concave up, right? So let's look at let's look at y prime first. What's y prime? 4x cubed. Now, we have a critical point here. What if 0 is equal to 4x cubed? Where is my critical point? X equals what? 0. Is that a max or min? How do you know? So if I do my little line graph that you get no points for on the exam, I might give you points because I think it's a good tool. So here's x equal to 0. And 4x cubed, if I put in a positive 1, is this positive or negative? Positive. If I put in negative 1, negative. Now what does that tell you about my function? My function is decreasing, then increasing. So it's coming down like this and this, so I have a what here? Minimum. And you would say, and I do the reasons first though, y prime goes from negative to positive. Because when I do the reason, then it tells me what I want to look for. It tells me what I want to look for if I do the reason first. And then I don't forget to do the reason. Okay, so we have a minimum. What's true about y double prime? It's equal to what? Take the derivative, 12x squared. Do I have a critical point? Sure. This is a candidate for an inflection point. What's x going to be here now? X equals what? 0. But for an inflection point, the second derivative must change sign. What is true about x squared? It's always greater than 0, positive, however you want to say it. So this is always concave up. Just because the second derivative is 0 doesn't mean you get an inflection point. I did get 0 here. But I don't have an inflection point because 12x squared is always greater than 0. I don't have a sign change. The critical points are the points where any function is 0. It's a boundary. It's where a derivative could change sign or a second derivative could change sign. You need a sign change for an inflection point. Yes? No sign change. Yep. And that happens, by the way. It happens on the exam. They'll say, is there an inflection point? Why or why not? And then you say, no, there's no inflection point because I didn't get a sign change. Now, you have to be particular about it. You have to say because the second derivative didn't change sign. You can't use it, or you can't just vaguely talk about things. Okay, that's it. The first derivative test, define max mins, concavity. We talked about increasing and decreasing functions, and then we talked about inflection points. And for some reason, it's not in my handouts. But then on Monday, we will do the second derivative test. You have a quiz on this on 4.1 through 4.3, so we'll pull it all together on Monday. And then and we'll probably get you started on max min problems on Tuesday as well. And that's what we're going to do the rest of the week next week. 4.1 and 4.2, we have the extreme value theorem, we have mean value theorem, and that's also on the quiz and mean value theorem, so I'll review that. I have a little opener for you guys. And then the derivative test. It's really, when you look at how many pages are written in the book, it really isn't that long. And you've had work time. So let's try a problem, and let's do more than what they ask. Now, we aren't going to do the second derivative test today, so just hold that thought. Okay, ready? Here's my function. Find relative max and relative minimum values of the function. Now, you should know what a cubic function looks like. Declan, do you know what it looks like? Cubic. So it could have some bumps there. There's a cubic function. Are there any global max or min if I'm going from negative infinity to infinity? No. That's what I mean by if they don't close the interval, Noah, that you have to know what the function looks like or you have to graph it if you're looking for a global. If I were to close that, put it on a closed interval, I would find both global max or global min. But I have some relative ones. In this neighborhood, that's a max. In this neighborhood, that would be a min. So let's see if we can find them. So I have f of x is equal to 4x cubed minus 3x squared plus 8. So what's f prime of x? 12x squared minus 6x. And I'm looking for critical points. Is this derivative ever undefined? No. This is kind of nice, actually. And I'll be honest. I mean, some kid came in this morning with asking for help on the assignment yesterday. If you haven't tried it, some of the algebra is really tricky. So you might bring in questions for me, and we'll go through it as a class. But I have another critical point when f prime is equal to 0. So 0 equals 12x squared minus 6x. Now, we're going to factor that, but be really careful. Always multiply back out to make sure you did it right. What's the greatest common factor? 6x. And then this is what? Just x minus 1? Or 2x minus 1? Okay, see what I'm talking about? So easy to lose that 2. So check. It's easy to check. Just multiply that back out. Do I get 12x squared? Sure I do. So either x equals 0 or 2x minus 1 equals 0. So I have two critical points. And we're just going to ignore that for right now. Maybe I can put it up here. So x equals 0 or x equals what? 1/2. So I'm going to do my little graph. Here's f prime. These are my critical points. And because these are zeros, I know I'm going to have a nice, smooth function. If I have undefined, then I don't really know. I could have a vertical tangent. I could have a discontinuity. I could have a sharp corner. I don't have to plug in anything because I know that that's a parabola, right? I'm going to be clever. You're right. You'd have to plug in a value in between there. But I'm lazy. I know it's a parabola. So it's anytime my f prime is above the axis, it's positive. It's negative. The derivative is positive there. So now I can actually draw a picture of what this function looks like. What's happening here to the left of 0? The function is what? Increasing. Told you it's 0, so it's smooth. Levels off, and it starts decreasing, and then it increases. So this is what? Max or min? Max. How do you know it's a max? Because f prime does what? Plus 2 minus. What about this other one? Okay, this is a min because f prime goes from negative to positive, and that's what you say. It's good enough. You don't have to write a whole sentence. I prefer not a sentence. They didn't ask for concavity, but we could do concavity and find an inflection point because this is a nice problem, actually. So my f prime, whoops, is, I'm going to write it down here, f prime equals 12x squared minus 6x. And I want to find what? For concavity, I need what derivative? Second derivative. That's all it tells me. So it's f double prime. 24x minus 6. I'm looking for possible inflection points. That would be where this is 0 or undefined. So this is 0 when x is, careful, it's not 4. It's 1/4. So x equals 1/4. That's a candidate. I don't know. I don't know if it's an inflection point quite yet. Sorry, that's in the way. Okay, so I'm going to do a little line graph again. You get no points for that on the exam, but I have 1/4 here. This is 0. What am I looking for? A sign change. That's it. So, you know what? That's a line. I can test regions, or I can know it's a line with positive slope. So my second derivative is positive, negative. Inflection point. And what are you going to say? because F double prime changes sign. Yes, sure. But you have to say it either goes minus to plus or it changes sign. Then you don't even have to show this. Do not have to show that. Yes. It doesn't matter because they're not going to look for that. They're only going to look for that you have an inflection point at 1/4 because F double prime changes sign. That's all they're going to grade you on. They will not grade you on that line chart. Some of you could put in values and just test it numerically. It's fine. Doesn't matter. They don't look at it. Okay, yeah. What's the concavity while we're here? Almost looks like a Nike symbol. It's concave down and it's concave up. But I already knew that. Because remember, I told you if this is 0, it's always going to be smooth. And guess where the inflection point is? It's right there. And guess where that is? My picture's not too bad. 1/4. They're usually going to ask you where on these, not what. That's it. So it's not that bad. And when I'll pull it all together next week. What do you want me to do? Yes. And they didn't ask that in this question, but I wish I had. I should fix my notes for next year. Okay. Now we are going to work on, this is from F prime to F. This is the derivative graph. It is not the function. Give you a little push start here. And I answered the question why first. Okay, girls? Now it's you girls. How do you know if the function is increasing? Colin, how do you know if f of x increases? What's it? F prime is greater than 0. Now, let's look at this. Oh, I'm going to use this little shade here. Now, where is f prime above 0? There it is. I'm not looking at the slope of these lines. I'm looking at where f prime is positive. Then when I want to do f prime negative, I'm going to cover this up, and it's going to be this little region right there. Do you see the difference? Did that help with the visual? So it's positive all the way from here to here. Then it goes negative. Then it's positive from here. Is it positive at 5? No. So guess what? You can't include 5. Is it positive at 6? Yes, you include 6. Do I know anything beyond 6? No. Don't go beyond the domain they give you. Unless they give you arrows. They won't. It's going to be a limited domain. Okay, girls, give it a try. That's what we're going to do, and hopefully we'll get it done. No, you answer the questions, and then you'll know how to draw it.